This is an Algebra 2 class where we're looking at exponential decay functions and their graphs. The exponential function of the form y equals a times b to the x will have a graph that's a decay graph when the factor, the base of our exponential part here, b to the x, when b is between 0 and 1. So the first thing we want to do is to recognize whether graphs of functions will be growth or decay graphs. So let's look at 3 examples. In number 1, we have y equals 4 times 5/3 raised to the power of x. Our value of b, our base, is 5/3, which is greater than 1. Since it's greater than 1, this graph is going to be a growth graph. In number 2, our value for our base, b, is 2/5. 2/5 is less than 1. Since that's less than 1, then it will be a decay graph. Our next example is a little bit tricky. We have a base of 5/4, but it's raised to the power of negative x. Using our properties of exponents, this function can be rewritten as y equals 2 times 4/5 raised to the power of x. So our base here is really 4/5, and 4/5 is less than 1, so this will be a decay graph. Now let's take a look at what graphs of exponential decay functions look like. We're going to be looking at 3 examples of exponential decay graphs, and in each one we want to find the domain and range. In addition to that, we're going to identify the horizontal asymptote. We're going to state the parent function and describe the transformations. So in this example for number 4, we have y equals 3 times 1/2 raised to the power of x, and then plus 2. Our parent function is where we're actually going to start with this. Our parent function is the equation y equals the quantity 1/2 raised to the power of x. So let's get a couple of points for this graph. We're going to go for values of x from -2 to 2. Remember, when we raise something to the negative power, we want to flip the numerator and denominator. We want the reciprocal. So 1/2 raised to the power of -2 is the same as 2 to the second, or 4. 1/2 raised to the -1 is the same as 2 to the first, which is 2. And then anything to the 0 power is 1. 1/2 to the first is 1/2, and 1/2 to the second is 1/4. Okay, and as we're looking at that, we also know that our domain for all exponential functions is going to be all real numbers. We're going to go ahead and do the graph of this parent function. We're going to do the transformations, and then we'll take a look at what the range will be. So as we look at our equation here, well, let's do our graph here. So -2, 4. -1, 2, 0, 1, 1, 1/2, and 2, 1/4. As you're drawing these, make sure that we know that it grows exponentially here. It's going to get steeper and steeper as it goes. We don't want to have this graph go off in a line. It's not going to be in a line. It's going to get steeper and steeper as we go. So we're going to be heading up this direction. And then when we come down, we're going to slide in very close to the x-axis, but not pass it. So again, when you're drawing your graph, make sure that you indicate this exponential curve that's going on. Okay, so this is our parent function. And now let's take a look at our equation. We see that we have 2 transformations. We have the multiplying by 3 and the adding 2. So multiplying by 3 is a vertical stretch. Of 3, and a vertical translation up 2. So let's do each one of these transformations, starting with the vertical stretch of 3. I'm going to take each one of these y coordinates and I'm going to stretch them by 3. That means I'm going to multiply it by 3. Well, at this one right here, we have a y-coordinate of 4, and 4 times 3 is 12. That's not going to be on our graph here, so we're going to kind of leave that one out. We go to this next one, our y-coordinate of 2. 2 times 3 is 6, so I want to go to 6. And here we have a y-coordinate of 1. 1 times 3 is 3. A half times 3 is 1.5. A quarter times 3 is only 3/4. Again, as I draw it, I know that I'm going to get steeper at this end here. It's going to grow very quickly. It's going to go up fast. We're going to come down, slide in next to the x-axis. Okay, now we're ready to do our translation up 2. So every y-coordinate is going to be moved up 2. So moving up 2 on all of these coordinates. In addition to all the coordinates going up 2, before when we move down, we slide in next to the x-axis when y is 0. So that's also going to be moved up 2. So instead of sliding in next to the x-axis at y equals 0, we're going to slide in at y equals to 2. So let's draw then our graph, making sure on one end we go up steeper and steeper, on the other end we get flatter and flatter, closer and closer to our horizontal asymptote. And that gives us our horizontal asymptote of y equal to 2. We also now see that our range, all of our y values are greater than 2. Okay, let's go to another graph. Starting again with the parent function. Our parent function this time is y equals 2/3 raised to the power of x. So that's the quantity 2/3. When you're using parentheses, all of 2/3 needs to be in the parentheses and the whole thing to the power of x. Okay, so let's graph some points here. Again, we're going to start with -2 and go to 2. Raising to the -2nd power. Remember, it's a reciprocal and squaring those, so this will be 9/4, which is also 2.25. To the -1st power, we end up with 3/2. Anything to the 0 power is 1. And raise it to the 1st power and the 2nd power. Okay. So let's go ahead then and graph these points. At -2, we're at 2 1/4. At -1, we're at 1 1/2. And then at 1, 2/3, and finally 4/9. This, as we look at this, gosh, it almost looks like we're in a straight line, but we need to keep in mind the shape of our exponential graph. On one side, we're going to slide in next to the x-axis. On the other end, we're going to get steeper and steeper as we go, and so our graph is going up. Now let's take a look at what transformations we have. As we look at it, we have the x plus 1. This is a horizontal translation. Remember, horizontal transformations always go opposite. So this one is going to be left 1. So we're going to move to the left 1 unit. And then we have the -3. That's our vertical one. So this one is going to go down 3. Since both of these transformations are just translations, we can actually do them in one step. We're going to take each point and we're going to move it left 1 and down 3. So here we're going to go left 1 and down 3. Again, left 1 and down 1, 2, 3. Left 1, down 3. Since we moved everything left 1 and down 3, our asymptote, our horizontal asymptote, which was at y equals 0, is also going to be moving down 3. So that asymptote, where we're going to get snugged up against on one end of our graph, is also down here. So as we draw our graph, we're getting closer to the line y equals -3 on one side. And on the other side, we're going to get steeper and steeper as we go. Make sure your graph looks like that. Okay, domain and range then. Our domain again, always on exponential functions, is all real numbers. And our range, since we moved everything down 3, is now y greater than -3. Okay, let's do one more. This one is going to involve a reflection, so it's good to look at this one. Our parent function, we look at our base of 1/5. So our parent is y equals 1/5 quantity to the power of x. Again, we're going to look at the same 5 values for x. When I look at these, I take 1/5 to the -2nd. That's the reciprocal raised to the second power. That's going to be 5 to the 2nd, which is 25, and that one's not going to show up on our graph. Using -1, we get 5. 0 is 1. 1 is 1/5, and 2 is 1/25. Very, very close to 0. So let's graph these points starting with -1, 5. And we have 0, 1, 1, 1/5, and 2. Oh, we're just barely above the x-axis there. Notice how steep this graph is, how quickly it grows on one end, and draw that a little better here. There we go. Grows on one end and shrinks on the other, decays on the other. Okay. Our transformation here, we have a multiplying effect of factor of -4. So because it's negative, this represents a reflection over the x-axis. At the same time, we're multiplying by 4, so this represents a vertical stretch of 4. So as we're looking at those, each one of our y-coordinates then is going to end up being multiplied by -4. So as I look at this y-coordinate of 5, 5 times -4 is all the way down at -20. That's not going to be on our graph. So let's go ahead and move down to our next point. Our y-coordinate of 1 multiplied by -4 is -4. And then I have 1/5 multiplied by -4, that's -4/5. And finally, 1/25 multiplied by -4 is -4/25, which is about a sixth. It's not very far below that x-axis. Again, keep in mind the shape of the graph. It looks like I could just graph those and put those and force them into a line, but that's not the shape of an exponential graph. We know on the right side here, we're going to snug in close to the x-axis, close to y equals 0, and then we're going down very steeply. Remember the point that we didn't graph? 5 times -4 is -20. I need to be heading very steeply down so that I could possibly reach -20 off on this end. So this is a very steep graph on one side, very flat on the other. The domain, once again, all real numbers. The range this time, because we flipped it over the x-axis, is y is less than 0. Okay, let's look at an application. In a decay function, the amount decreases over time. We saw that in our graph. As we moved left to right, the values went down towards 0, or whatever your horizontal asymptote was. A percent decrease can be modeled by an exponential decay function. Our decay factor, the b, is equal to 1 minus a percent decrease, or b equals 1 minus r, where r is the percent in decimal form. Let's look at an example of that. We want to write a decay model for the following. So you buy a new car for $28,500. It depreciates in value. That means the value goes down 18% per year. And we want to find our decay factor. Well, our decay factor is b, and that's going to be equal to 1 minus r. So the first thing I have to find is r, the percent decrease in decimal form. So r is 18%. In decimal form, that's 0.18. So our value for b is going to be 1 minus 0.18, or 0.82. That's our decay factor. The initial value is easy. The initial value of our car when we bought it before any time has gone by is $28,500. So A is $28,500. So we want to write our decay model. Remember, our decay model is of the form y equals a times b to the x. So we have our a, we have our base. We're just going to plug those in. Y is equal to 28,500 times our decay factor, 0.82 to the power of x. Now we want to use the model to find the value of the car when it's 5 years old. So we're just going to put 5 in for x. So y is equal to 28,500 times 0.82 raised to the power of 5. And when we do that, we get our value after 5 years is $10,566. And those are exponential decay functions.